Hello everyone, welcome to the session about advancing diversity and inclusion in voice AI with the speech disentanglement technology. I'm Eva Kolczyk, I'm Software Development Manager at Amazon.
And I'm Kayoko Yanagisawa, Senior Speech Scientist at Amazon.
I will start with explaining why diversity and inclusion and equity is important in voice AI. What are the challenges, how are we approaching them, and what is our vision for future? Then Kayoko will give you text-to-speech overview and will introduce you to speech disentanglement technology. And then we'll explain how it's employed in different products for the customers. So we live in the diverse world, and our technology should reflect it. It should not perpetuate biases. Instead, it should minimize and prevent them where possible. Diversity has multiple dimensions. There is race, ethnicity, age, gender, physical and mental ability, and language, and more. In Alexa, we acknowledge and embrace speech and language diversity. We create equitable experiences for our customers, regardless of their speaking style, language spoken, and accent. All ends with the experience that is inclusive for everyone. Why it's important? As the voice AI surrounds us and helps us every day, it has impact on our life in both direct and indirect way. The first impact is a very direct result of voice AI functions. As we use voice AI every day, it improves our efficiency, it helps us cut the costs. So looking at it from the equity perspective, we have to ensure that it supports all groups of people in the same way. Because if it works better for one group of people than from the other, then we are moving away from our goal of equity. Let me take an example of the speech recognition system. If it works, for example, used for dictating emails or notes, if it works better for one group of customers, then they would have a time advantage over others. It wasn't really a random example. Stanford research shows that common speech recognition systems have a 16 percentage point gap in accuracy between white participant voices and black participant voices. That means in real life that if a white person uses speech recognition system to dictate emails, they will have to correct only, let's say, 10% of the text and can go off to other tasks, while the black user will have to correct 26% of the text and will be stuck with this task for much longer. These are small things, but they add up. Think about how many emails you write. It can go further, and AI can even harm some groups if it's built based on biased data. It would then perpetuate the inequalities from the time when the data was collected. We have seen examples of such cases in machine learning systems supporting judicial systems or mortgage qualifications. But even voice-related machine learnings have impact. For example, they are used for language fluency exams. It turns out that a fluent English language speaker with a strong Irish or Scottish accent can fail such an automatically graded exam because the speech recognition system cannot understand them well, even though they are perfectly fluent in English. There is also the second angle to look in a more indirect way at the impact of voice AI. In 1990s, Stanford researchers found out that individuals exhibited similar behavior towards TV sets and computers as they did towards other humans. Not only did they treat these machines with respect, but they also interacted with feminine-sounding and masculine-sounding computers differently, based on gender stereotypes. People are treating voice AI assistants even more as other humans than they do with TV sets. For example, they assign them gender even when the tech owners are aiming for the genderless experience. Based on that, and based on other research, the 2019 UNESCO report concluded that the prominence of the feminine-sounding voice assistants is perpetuating the stereotype of women as submissive and compliant. And the UCLA professor, Sophia Noble, said that this technology can act as a powerful socialization tool that is teaching us, and in particular our children, of the role of women, girl, and people gendered female to respond to demand. So this shows how strong the impact can be. Now let's talk about the scale. As the voice AI sector grows, it is more and more important to be thoughtful about all effects, even the secondary effects it has on our lives. There are 140 million Americans using voice AI. And by the predictions from Statista, in a couple of years, there will be more devices with voice AI enabled in the world than people on this planet. That's a huge scale. And then there is the generation growing up with voice AI always present in their homes and their hands. 7 years ago, when we bought our first Echo device, my younger son was 5, and he's using Alexa every day since then. I think that makes him a native user. Because of the strength and the scale of the impact, we have to put all our efforts to ensure that voice AI is fostering diversity, equity, and inclusion. So how are we doing with this challenge? Let me start with a few examples how Alexa and other major voice AI is addressing the gender diversity gap. It didn't start all perfectly. Traditionally, all major voice AIs have been featuring feminine-sounding voices. Since then, we have launched a masculine-sounding voice in Alexa, giving customer the choice of voice. And we have also launched another wake word, the Ziggy, in addition to Alexa, Echo, Computer, and Amazon. That all helps us to move away from the stereotypes associated with the wake word or voice. It is also vital to point out how voice assistants are responding to harassment and verbal assault. Based on Robin Data Labs, it shows that at least 5% of digital assistant inquiries are sexually explicit in nature. And that's only what the algorithms can catch. So we know that the voice AI functions as a powerful socialization tool. So it's really important how it answers to those harassment comments. Because having a positive or negative response to those harassment comments, it can perpetuate the idea that it's appropriate or inappropriate to make those comments in the offline real life. It is especially important when we remember that people associate gender with the voice assistant and alter their behavior based on that. Example from the past, one of the major voice AI systems responded to a really strong sexual slurs with the phrase, "I'd blush if I could," welcoming verbal assault with flirtation. Since then, it has been improved. All major voice AIs have corrected their responses, often simply refusing to respond to verbal assault. What about outside of gender? How are we embracing and supporting people speaking different languages and different accents? How are we allowing them to leverage the benefits of voice AI, regardless their preferred language or speaking style? It is an important question, and let me use one example to illustrate that. It's estimated that about 80% of American population, which translates to 60 million people, is speaking both English and Spanish. So how are we supporting those multilingual households? We made a good progress there too. We support 17 languages and variants, we have also launched dynamic language switching system, which enabled multilingual mode. This mode allows customers to interact with Alexa in their preferred language and then get answers in the same language that they asked the question, initially still using a different voice. We started with Indian English and Hindi pair, Canadian English and French, and US English and Spanish. And since then, we have now 15 pairs of languages where the multilingual mode is supported. We have also improved how it functions. In 2021, we have launched the solution that allows Alexa to respond to you in different languages, but still using the same voice across those different languages, improving the fluency of the experience. We have started with US English and Spanish, and we have added Canadian French, German, and UK English to the mix since then. This feature addresses two main pain points. It allows customers to interact with Alexa in their preferred language within the same household, and it also allows customer to respond, to provide back the local content in a native fluency, in a native intonation. So that makes this experience inclusive for all the members of the family in the bilingual household, where they can all enjoy their interaction with Alexa regardless of their preferred language. The technology behind the multilingual mode will be explained later in this session. Another aspect of diversity and inclusion is supporting people with different mental and physical disabilities to be efficient in their everyday life. There are 14 million people in America who have different level of visual impairment, of which 3 million cannot be corrected with glasses or lenses. Voice AI helps them, reading for them web pages, apps, or documents. We have also launched a feature to support these people called Show and Tell, and this feature helps them to identify common food products that are packaged in a way that makes it difficult to recognize by touch, like canned goods or boxed food. So all you need to do is to hold the product in front of your Alexa and ask Alexa, what am I holding? And then Alexa will provide you the clues to position the package in front of the camera, and then will identify the product for you. Voice AI is also a huge help for people with other cognitive disabilities, like dyslexia, impacting over 30 million of Americans. There are also people who cannot read or cannot read well. Even in America, it's estimated that over 30 million people are illiterate. And then another 21% cannot read at grade 5 level or higher. Voice AI is supporting inclusion for these people with different educational background. We also want to be ready and support the next generation. And kids' expectations are much higher. They want us to speak slower and more expressively to stay engaged. To support this need, we have launched a feature called Reading Sidekick, which supports kids when they learn to read. We have also introduced features where Alexa can be more helpful for people who are hard of hearing. If they cannot comprehend Alexa answers at the standard speaking rate, they can change the speaking rate so that Alexa speaks slower, which makes it easier for them to understand. It can also be helpful for people who are learning new language using Alexa. So with these examples, you can see how the text-to-speech technology can contribute to fostering diversity, equity, and inclusion by removing barriers imposed by location, education, physical ability, or social status. And we want to move further in this direction in future. How can we do it? For example, text-to-speech technology can also support speech recognition systems. We would like to be able to recognize, to understand every sort of voice, regardless of language, accent, speaking style. But we have to remember that the speech recognition systems are trained on a large data sets of annotated audio data. So to be able to understand all those languages and accents and styles, we would need to have those large data sets from those different diverse groups. Those data sets are not available, and creating them by recording with all the different languages and accents and styles would be too expensive. But what if we could use the text-to-speech technology to create a purely synthetic voices in all different languages and accents and styles, and then use those text-to-speech models to generate the data for the automatic recognition systems? The speech disentanglement technology that will be explained later in the session is a huge step in this direction. What else? We would like to be able to create high-quality voices of any language, style, and accent, and expressiveness, so that the voice AI can sound like anyone who is using it. Before I explained how we want to remove perpetuating the gender stereotypes by having only feminine-sounding voice assistant voices, that is true. But there is also the other way to look at it. The voice AI assistants are super smart. They have these superhuman abilities. They can speak as many languages as no human can. They can do math like no one can. They know as many facts as no one can. So when I look at the voice assistant from this perspective, I like when it has feminine sounding voice. I like to think about it as a superwoman, super smart woman. But then we have all those different dimensions of diversity coming into place. So we would like the voice AI to be able to speak like any user, so that when you personalize it, you can see someone speaking like you, regardless whether you're from Boston, Atlanta, or Texas, or Ireland, or Scotland. This is still a long-term vision for us, but it guides us in our efforts every day. I hope with these points on importance to make voice AI inclusive and diverse, I build up the momentum for the next portion of this session, where Kayoko will explain the science and technology behind the text-to-speech features that are fostering diversity, equity, and inclusion. Thank you.
Thank you, Eva. So let me now take you through some of the technologies that we have developed using machine learning to advance inclusivity in various areas. Before that, I'd like to start by explaining what text-to-speech is and how it works. In the Alexa scenario, in a nutshell, TTS is the technology that generates the voice that you hear from devices such as Amazon Echo. When you ask Alexa to play a song by Lady Gaga, you say Alexa, or you use one of the other wake words. And when the wake word is detected, the blue ring lights up, indicating that Alexa's listening for your request. Your request first goes through automatic speech recognition, which turns your speech audio into text. Then natural language understanding converts or interprets the text into an action or set of actions that can be performed by Alexa. So for example, the request your request is interpreted as a play music intent by an entity called Lady Gaga, and it acts on that. At the same time, you will hear the Alexa voice saying, playing songs by Lady Gaga. The voice that you hear is generated by TTS. The aim of text-to-speech is to go from text to speech. In the neural TTS framework, there are three main components to this flow. First, we have the front end, which analyzes the text linguistically and converts the text into phonemes, which is a symbolic representation of the sounds. This consists of several types of linguistic analyses. For example, the sequence of digits 1991 might be pronounced 1991 if we're talking about the year, or 1,991 if we're talking about the amount in dollars, or even 1,991 if it's a British English voice. So the front end is language specific. And in languages like Japanese, which don't have spaces between words, we even have to predict the word boundaries. The front end can also handle abbreviations and acronyms. So the letters DR in Doctor Who is pronounced doctor, but in Manhattan DR, it's pronounced drive. The front end includes a grapheme to phoneme module, which converts the sequence of characters into the phoneme representation. So the final output of the front end module is a sequence of phonemes on punctuations. Then the next component is the acoustic model. Here, we convert the symbolic representation of sounds into an acoustic representation called spectrograms. The spectrograms are a representation of how the energy in different frequency bands change over time. So the x-axis is time and the y-axis is frequency. In the time axis, the spectrum of the signal is analyzed in small time windows called frames. A frame might be 50 milliseconds, for example. And in the frequency axis, the filters of a human ear are not linear. They're biased towards the lower frequencies. So to replicate that, the frequency axis is in a Mel scale representation. And in the image here, you see higher energies represented with a brighter pixel. And those are, in a numeric representation, these frequency bins would be represented with larger values. The spectrogram can tell you a lot of information about the spoken content, but not only that, it can also tell you how the voice goes up, the voice pitch goes up and down. So, for example, if you pronounce different vowels, I, O, on a monotonous pitch, you can see the spectral shape changing over time, as in the spectrogram, the leftmost spectrogram at the bottom. You can also see the pitch changing. So if I go, ah, you can see the lines going up at the end in the middle spectrogram. And these are the harmonics. There doesn't seem to be much going on in the higher frequency regions, but in fact, this portion contains a lot of information that contributes to the naturalness of speech. And the last spectrogram is me going, the cat sat on a mat. So you can see that there's a lot of information encoded in a spectrogram, and that's why we like to use these as an acoustic representation of speech. The last component is the vocoder. So I mentioned that the spectrogram is an acoustic representation of speech, but it's only an approximation, and some information is lost on the way. For example, the spectrogram captures the energy of the signal, but the relationship of frames through time, called the phase, is lost in the spectrum representation. The vocoder is able to reconstruct this information and generate a high fidelity signal. So this was the third component. So when we met at REMAS back in 2019, we took you through these three components already. This NTTS architecture made it possible for us to further disentangle various aspects of speech and to embrace vocal diversity, foster inclusion, and produce speech that enables and produce speech that makes Alexa's magic work optimally for everyone. So in the remainder of this talk, I'd like to tell you a bit about the work that we've been doing to achieve this. So what is speech disentanglement? Imagine you get a phone call and you answer the call. The voice on the other end says, "This is me." Just from this very short phrase, you immediately know that it's your mum. She's got a cold, but she sounds very excited. The speech can tell us a lot of things about the person speaking. Human speech is produced by the airstream coming from the lungs, which passes through your larynx, and then it's modified by articulators in the mouth and the shape. And because speech is a result of movements of these organs, speech can contain a myriad of information which are indicative of the speaker, like the age, emotion, gender, and so on. Some of these, like age and physique, are intrinsic to the speaker, whereas some others, like emotion, are volatile. And I say contain in double quotes because I don't mean to say that we can determine someone's age or emotion just by listening to their speech or by analysing their speech. But human listeners are quite sensitive to these details, and often we have a rough idea of whether a speaker is a young person or an old person, whether they're sad or happy, or whether they've got a cold because they've got a blocked nose. You can tell that it's your mum on the other end of the phone, even if she's super excited or super sad. You can probably tell that it's her, even if she's got a cold or if she's speaking another language. In other words, emotion and speaker characteristics are two aspects of speech that can be disentangled or separated. We view speech like a rope constructed of a complex weave of individual threads, where each thread contributes to a signal, where each thread contributes to an aspect of a signal, like age, emotion, gender. And the sum of the entangled threads produce what we perceive as speech. The goal of disentanglement is to tease apart these individual threads. The goal of speech disentanglement is to tease apart these individual threads so that we can individually modify them and reweave them into a completely new signal. In the past, we used to concatenate fragments of speech to synthesize speech, which meant that we were limited in our ability to only modify one aspect of speech, such as keeping the speaker characteristics, but modifying the emotion or accent. But thanks to neural TTS, we are now able to generate speech which have not been seen in the training data. And this technology allows us to disentangle various aspects of speech to create various voices in various languages, accents, emotion, and so on. So let me start by introducing you to Polyglot, which is a multi-speaker, multilingual TTS model which enables any voice to speak any language. Here, we're disentangling the speaker and language aspects of speech. Typically, a TTS voice is trained by recording hours of speech from a single voice talent in a single language. The resulting voice can only speak the language it was recorded in. And as a result, you may have noticed that Alexa has a different voice in different languages. Some voice, like the Indian English Alexa voice, has bilingual recordings in Hindi and Indian English. So we were able to develop a bilingual voice with bilingual recordings from one voice talent. However, as we expand the number of languages, this becomes impractical. It's impractical to find a voice talent who has the voice characteristics that match the Alexa persona and speaks all the languages required. The solution to this was Polyglot. We train a model with recordings of multiple speakers in multiple languages, each speaker only speaking one language. And with this, we launched the American English Alexa voice speaking English and Spanish, supporting bilingual households. With this mode enabled, if you speak to Alexa in Spanish, Alexa will respond to you in Spanish, and if you speak to Alexa in English, Alexa will respond to you in English in the same voice. So let's have a listen to what it sounds like.
Hi, I'm the American English Alexa voice. I recently learned to speak Spanish fluently. Here's a sample. Muy bien, puedes activar los permisos en cualquier momento en la aplicación complementaria.
We use the same technology to launch the masculine voice speaking US English, US Spanish, German, Canadian French, and UK English. The masculine voice option was launched to provide customers with more voice options and also to address gender stereotypes about AI voices being female. So this is what it sounds like.
Hi, I'm the masculine Alexa voice. My native language is American English, but customers from other countries can also hear my voice in their native languages. Here's US Spanish. Enseñando el pronóstico de Bogotá para la siguiente semana. Here's me speaking German. Morgen wird eine Höchsttemperatur von -5 Grad Celsius erwartet. Here's Canadian French. Selon Météo Média, il y a 30% de probabilité d'averse plus tard cet après-midi. And this is British English. According to weather.com, there is a 30% chance of rain later this afternoon.
So let's have a look at how the model actually works. You'll remember the three components of TTS I talked about earlier, which you'll see at the top right of the screen. The second component was the acoustic model, which predicts the spectrograms from the phoneme sequence. So we'll dive deep into this part because this is where the magic happens. To go from phonemes to spectrograms, the acoustic model is a sequence-to-sequence model consisting of three components: encoder, attention, and decoder. Sequence-to-sequence modeling techniques are often used for sequence-based problems where the input and output have different sequence lengths. In this case, the input is a sequence of phonemes and the output is a sequence of spectrogram frames, and they have different lengths. The encoder translates the phoneme sequence into a latent representation, which in a vector of, say, 256 dimensions, can encode the complexity of the phoneme sequence and relates the linguistic information, i.e. phonemes, to the acoustic information, i.e. spectrograms. The information is then sent to the decoder, which predicts the output sequence of frames. The decoder, in turn, relies on an attention module to weight the relevance of each key of the encoder output at each time step in order to generate the most likely spectrogram for the input sequence of phonemes. In other words, it tries to answer the question, how relevant is phoneme X for target frame 1, target frame 2, and so on. Now, normally, the model is only conditioned on phonemes because we train the model on one speaker speaking one language, so the model knows what speaker and language data it's seeing. For Polyglot, we used three additional inputs: speaker ID, language ID, and accent ID, so that for each sample seen in training, the model knows who is speaking, what the language is, and what the accent is. We use accent to distinguish, for example, Canadian French and European French. The information is concatenated with the phoneme sequence and input to the encoder, and it's also concatenated with the output of the encoder and fed to the attention model. At inference time, if we want speaker A speaking language X in accent Y, we provide the model with the corresponding speaker ID, language ID, and accent ID, and that way we can make any voice speak any language in the training data. So this is how we disentangle the speaker and language aspects of speech with Polyglot. An extension of Polyglot is found in the work that we're doing to create accented voices. The British English Alexa voice speaks an accent called received pronunciation, RP, which is widely regarded as the standard form of British English. So this is what it sounds like.
Hello, this is your British English Alexa voice.
However, as you may know, the British Isles are extremely rich in accents. We have some of the highest levels of accent diversity in the English-speaking world. And that means that, of course, our customers don't all speak RP. And studies show that the accents we trust the most are those which we are familiar with, which means that there is a need for accented English. If we want to generate a voice with an Irish accent, for example, we can use AI to create such a voice. One way of achieving this is to train a voice conversion model on multi-speaker, multi-accent English recordings. Then, using this voice conversion model, we convert the recordings of an Irish English speaker speaking Irish English to sound like the target British English speaker, but still speaking with an Irish accent. So let me play a sample of an Irish speaker speaking Irish English, followed by the voice conversion output, where this sounds like a British English voice, but still with the Irish accent.
Critical velocity is the speed that a falling object reaches when gravity and air resistance equalize on the object.
Critical velocity is the speed that a falling object reaches when gravity and air resistance equalize on the object.
So we generate a synthetic corpus of this British English voice speaking Irish English, and then we train a polyglot model with this corpus and all the English recordings that we used at the beginning. Here we use speaker ID and accent ID. To generate samples of the British English voice speaking Irish English, we input the speaker ID of this target British English voice and the accent ID for Irish English, and the resulting voice might sound like this.
The party last night was great crack. We got ice cream on the way home and we were happy out.
In an ideal world, we would want to make a voice that represents every person in the world and have the complete coverage. However, in reality, that is not possible. But we're working on technologies to build voices that rely on a diverse large data pool and has the ability to extract speaker-specific aspects of speech and represent them in the resulting voices. One such approach is a flow-based decoder that can define the mapping between the spectrogram and the latent representation. The inversible nature of the model means that we can encode the spectrogram into a latent representation and decode it back into a spectrogram. In order to perform speech attribute control, we can provide different conditioning to the model during encoding and decoding stages and perform voice conversion or accent conversion, or just use the decoding part to create new voices or voices with different attributes. For example, using American English accent embeddings at encoding time and Indian English accent embeddings at decoding time, we can convert an American English speaker to speak Indian English.
Here's a sample of the song that best matches the details I got from Pandora.
Here's a sample of the song that best matches the details I got from Pandora.
Similarly, you can control the speaker characteristics using speaker embeddings, and you can interpolate between different speakers.
Can we go to Disneyland? 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 Can we go to Disneyland?
Here, it's worth noting that the voices in between don't actually exist in the training data. They were generated by interpolating between the two speakers. We can also control different attributes separately. So, for example, we can control the gender and age group separately, so that we create a masculine sounding voice or a feminine sounding voice that sounds like a child or an adult.
Continue in this manner till the border is completed, arranging the sippets, pale and the dark one alternately.
Continue in this manner till the border is completed, arranging the sippets, pale and a dark one alternately.
Continue in this manner till the border is completed, arranging the sippets, pale and a dark one alternately.
Continue in this manner till the border is completed, arranging the sippets, pale and a dark one alternately.
So combining these together, we can create a wide variety of voices, speaking a wide variety of languages, accents, and with different emotions. Another aspect of diversity is age. Reading Sidekick is a skill which allows children to practice reading skills with Alexa. The voice used there is in a storytelling style, rendering the story as if a parent was reading a book to their own child, with a lot of expressivity to engage to provide children with an exciting and engaging experience. A user experience research study with children showed that the ebook style speech developed for reading books for adults was not suitable for children's book reading. Children felt that it was too monotonous, computer-like, and too fast. They were not able to follow the storyline when Alexa was reading, and they got disoriented. On the other hand, they were delighted when Alexa used a more expressive speaking style. So we developed a style that speaks more slowly and with more expressivity. It's still the same Alexa voice, so here we're disentangling speaker and style, and we're addressing age-based inclusivity to help children. So I'll play the standard Alexa voice, which you'll hear when you ask for the weather, for example, and then the reading Sidekick voice.
Girls and boys, come out to play. The moon doth shine as bright as day. Leave your supper and leave your sleep, and come with your playfellows into the street. Girls and boys, come out to play. The moon doth shine as bright as day. Leave your supper and leave your sleep, and come with your playfellows into the street.
Because expressive speech is more variable than neutral speech, expressive speech models are prone to instability issues. So we applied various techniques to overcome this challenge. First, we removed overly expressive samples from the training data, and then we also added neutral data to the training to provide less extreme prosodic patterns for the model to learn from. And then the rest of the magic happens in the acoustic model again. This time, we have 3 new components, highlighted in orange here. To handle recordings in both neutral style and storytelling style, we added a style encoder. This helps the model to distinguish the 2 styles. Also, we want a different style for the dialogue and narration. For example, in Hello My Friend Said the Cat, we want a more expressive style for the part in double quotes. So we added a dialogue encoder to capture that. We also added a reference encoder. This encoder takes as input a reference spectrogram and is expected to capture any variations in the data that cannot be explained away by the conditioning inputs, which are the phonemes, style ID, and dialogue flag. We expect this encoder to capture variations in the intonation which are not sufficiently captured by a simplistic representation of styles in the form of a style ID. And thus we were able to train an expressive storytelling style to engage children. When we consider customer experience, accessibility is another area of inclusivity we consider important. Older customers, hard of hearing customers, or customers with cognitive disabilities may prefer Alexa's speaking rate to be slower. On the other hand, customers with impaired vision who are used to voiceovers and used to faster speaking rates, or people just looking for Alexa's responses to be more efficient, might prefer a faster speaking rate for Alexa. We have a feature in Alexa called the preferred speaking rate, where customers can speed up or slow down Alexa's responses based on their preference. This modification of speed is done in the vocoder component, which is the last of the 3 components of NTTS I talked about earlier. The vocoder takes as input the spectrogram generated by the acoustic model and outputs a waveform. The spectrogram has 80 samples per second, while the output waveform has 24,000 samples per second. This means that in order to achieve the same temporal rate of outputs between the 2 components, each spectrogram sample needs to be repeated 300 times internally. Now, if you want to modify the speaking rate, you can change this upsampling rate clock. So for example, to make Alexa speak 10% faster, we replicate each spectrogram frame 270 times instead of 300 times. An alternative approach is a digital signal processing technique, which we used to use before we switched to neural TTS, when we used to concatenate small fragments of speech. We could have used the same technique for NTTS, but our experiments showed that the vocoder upsampling approach generated higher quality speech than the DSP approach, and it resulted in more intelligible speech, even at higher modification rates. So here's an example of Alexa speaking with different speaking rates.
This is my normal speaking rate. I'm speaking twice as fast. I'm speaking twice as slow.
Another feature in which replacing digital signal processing techniques with machine learning saw success is the whisper mode. Imagine you're a parent trying to put your baby to sleep, and you ask Alexa the weather for tomorrow. Alexa replies in its normal voice, and the baby wakes up. A lot of you will know how annoying this can be. To address these customer needs, we launched Alexa Whisper Mode. When a customer whispers to Alexa, we use AI techniques to detect that the customer has whispered, and Alexa responds in kind by whispering the response back instead of speaking it out loud, just like how a human would respond in such a situation. With this feature, we address the inclusivity for families with small children, for example. Initially, we used the DSP technique to add whisper to the normal voice. This approach was rule-based, based on a large body of scientific literature analysing the acoustic differences between normal speech and whispered speech. However, we received feedback from customers that the resulting whisper was sounding creepy. So we then trained a deep neural network model, a voice conversion model, to convert normal speech to whispered speech. To do this, we used a parallel corpus of normal and whispered speech recordings from multiple speakers, and then we trained a DNN model to learn the general mapping from acoustic features of normal speech to those of whispered speech. Evaluations showed that this DNN model can produce more natural whisper than the DSP technique. In addition, because it was trained on multiple speakers, it could generalize on unseen speakers, which means that it could be applied to any speaker and still sound natural. So let's compare the two approaches.
Setting the temperature to 70 degrees Fahrenheit. Setting the temperature to 70 degrees Fahrenheit.
This second sample was the DNN-based approach, and you can hear that it's less metallic than the DSP approach, and this is the one that's used in the Alexa Whisper mode in production today. So we talked about how in Alexa TTS, we're using disentanglement technologies and other machine learning techniques to make Alexa for everyone and anyone. We talked about Polyglot, which is used to support multilingual households, and which enabled us to launch the masculine voice option in 5 locales, addressing gender stereotypes about AI speaker voices. We also talked about how we're addressing the needs of customers of various ages. So reading Sidekick, which helps children learn to read, and the preferred speaking rate, which helps elderly customers. The preferred speaking rate feature also helps customers who are hard of hearing or who have impaired vision. Then the whisper feature advances inclusivity in terms of family and lifestyle. There are several other features we didn't get the chance to talk about today, but we're working hard to make interaction with Alexa a delightful experience for everyone and anyone. As Eva mentioned in her part of the talk, there are many more aspects to DEI. We want to create experiences for customers that are accessible and usable by as many people as possible. So we'll continue working to make the world a better place across these stereotypical boundaries. Thank you.